To formally introduce myself, my name is Leo F. Martin, Jr. I'm a licensed master electrician, currently licensed in 18 states. I'm a former member of the Massachusetts Electrical Code Advisory Committee. That's the committee that puts together the amendments, the Massachusetts amendments to the NEC. I'm a current member of the Massachusetts Electrical Code Interpretations Committee. I'm a current member and former chairman of NFPA 72, the National Fire Alarm and Signal Code, Chapter 27 Committee, which covers public emergency alarm reporting systems. I'm a former member of the International Brotherhood of Electrical Workers, and I've been an instructor of electrical code and theory beginning in 1987. Every electrician, over the course of their career, will have to go to the code many times to find out what size conductors are required for a given circuit. Conductors are required to be selected based on the installation conditions specific to that given circuit. The code does have ampacity tables that can be used. However, the ampacities in the tables generally must be adjusted to reflect the actual installation conditions. One of the most referenced sections of the NEC is section 310.16, along with its accompanying table, table 310.16. Table 310.16 is also one of the most misused tables in the entire code book. This table is used when you're installing your conductors in a raceway, a piece of pipe, when you're trying to size up a cable, or if you're installing your conductors direct buried in the ground. The ampacities in this table are used as a starting point when calculating conductor ampacity for a given circuit. Section 310.16 states four very specific installation conditions that must be met in order for the table ampacities to be accurate. What are those four conditions? Well, condition one, the conductors have an insulation that has a voltage rating of between 0 volts up to and including 2000 volts. Condition two, the conductors have an insulation that has a maximum operating temperature of either 60 degrees C, which is 140 Fahrenheit, 75 degrees C, which is 167 Fahrenheit, or 90 degrees C, which is 194 Fahrenheit. Condition three, the conductors are installed in an area that has an ambient or surrounding air temperature of about 30 degrees C, which is 86 degrees Fahrenheit. And the fourth condition states that there are not more than a total of three current carrying conductors in the raceway, in the cable, or if you're going to be bundling more than two multi-conductor cables together for longer than 24 inches without maintaining spacing. Now, that term, maintaining spacing, is not defined in the NEC, but you can apply common sense to understand the intent. Now, the code does include requirements for securing your cables at set intervals. Cable wiring methods are probably the most common way that branch circuits are installed currently. If you're wiring a dwelling unit, depending upon the part of the country that you're in, you're probably going to be using non-metallic sheathed cable or Romex. For a commercial job, commercial fit up, many times you're using metal clad cable type MC. Now, you pull your cables and then you go back and you want to properly secure them. If you have multiple cables, many times you tie wrap them or use bridle rings or whatever method of support you happen to be using. But if you're going to bundle those multiple cables together for longer than 24 inches without maintaining spacing, well, the conductors, the cables in the middle of that bundle, won't be able to release their heat into the surrounding air. The heat will be entrapped in the middle of that bundle. So what you have to do is that you have to go back and spread the cables out a little bit to allow air circulation in between all of the cables that are bundled together. Now, I understand that it might not, the end result might be that the installation does not look as neat as it would have if you had them all bundled tightly together. But your job has to be code compliant. And in order to be code compliant, you have to maintain some spacing between those cables to allow that heat in the inner cables to be able to dissipate. If the actual installation conditions differ from the four conditions stated in the table, well, then the ampacities from the table have to be adjusted. We usually call that derating. In many installations, the actual installation conditions do differ from the conditions stated above. Because of this, you must learn to properly adjust the ampacities from the table to reflect the actual installation conditions. Many installations will require you to install more than 3 current carrying conductors in your raceway or cable. Many times you will be installing your wiring in an area where the ambient or surrounding air temperature is above 30 degrees C, 86 degrees Fahrenheit. If either or both of these conditions exist, then the ampacities from the table must be adjusted to reflect the actual installation conditions of the circuit. Ampacity is defined in Article 100 of the NEC as the maximum amount of current a conductor can carry continuously without exceeding its insulation's temperature rating. A conductor's ampacity varies based on its type of insulation and the way it is installed. Mechanical abuse and heat are the two most common hazards that a conductor or cable must be able to endure. Conductor insulation can become damaged by excessive heat. Continued exposure to excessive heat will cause the conductor's insulation to become soft, begin to melt, and possibly even burn. Conductors are primarily exposed to excessive heat from two sources. There are more than two, but two primary sources. One would be the ambient or surrounding air where the circuitry or where the conductors are installed. Keep in mind, if it's 86 degrees Fahrenheit in the area where you're installing your wiring, eventually the wires will reach a temperature of 86 degrees Fahrenheit before we even allow any current to flow. The second source of heat will be the heat that will be generated within the conductors from the flow of electric current. Whenever current flows, heat's generated. So both of those sources must be considered when you're trying to determine a conductor's ampacity for a given installation. The maximum temperature rating permitted for a conductor is called its temperature rating. The conductor's maximum temperature rating will be reached when it's loaded up to its full table ampacity while being installed in an area where the surrounding air, the ambient temperature, will be about 86 degrees Fahrenheit, and there are not more than a total of 3 current carrying conductors in the raceway or in the cable. Now, the insulation's type letter is required to be marked on the conductor's insulation or on the outer cable jacket of a cable. This type letter indicates its maximum operating temperature and other applicable provisions. We've all looked at wires. We've seen marked right on them TW, THW, THHN, and so forth. What does that actually tell us? Well, if there's a T in the insulation designate, it indicates that the insulation is thermoplastic. If there's an R, it indicates that the insulation is made from a rubber-based material. If there's a W, it indicates that insulation is listed for use in a wet location. If you see an N, like THHN, that N indicates that the wire has a nylon outer covering over the insulation to add a little bit more mechanical protection to that wire. Now, if there's no H in the insulation type, then that wire has a 60 degrees C temperature rating. If there's one H in the insulation type, like THW, that indicates the conductor has a 75 degree, 167 degree Fahrenheit maximum operating temperature. And if we have two H's in the insulation type, it indicates that that insulation has a maximum temperature rating of 90 degrees Celsius, which is 194 degrees Fahrenheit, such as THHW or THHN. Couple of examples. We look at the insulation and we see it marked TW. What do we know about that insulation? Well, we know it's made out of thermoplastic, T, and we know that it's listed for use in a wet location as a W, TW. No H tells us that that wire, that conductor, has a maximum operating temperature of 60 degrees C, 140 Fahrenheit. If we see a conductor designate THW, what do we know about that wire? Well, we know the insulation is thermoplastic. There's one H, so we know it has a 75 degrees C, 167 Fahrenheit maximum operating temperature. If you see two H's like THHN, thermoplastic, two H's indicate a 90 degree Celsius or 194 degree Fahrenheit maximum operating temperature. And the N would tell us that that insulation has its nylon outer covering to give it the little bit of extra mechanical protection. One thing about THHN insulation, keeping in mind, THHN insulation is probably one of the most common insulations that we use these days. There's no W in that insulation designate, THHN. That means it cannot be installed in a wet location. Now, the code tells us that anytime we install our conductors in the ground, whether they're direct buried or installed in a raceway, any installation in the ground is considered to be a wet location. Therefore, the insulation on the wires that you install must have a W in the insulation designate. Now, a bit of a caveat to that. the manufacturers usually give the THHN insulation a multiple listing. So if you actually look at it, look at the wire on the outside, you usually what you'll see is it'll be marked THHN slash THWN. That THWN second designate permits it to be used in a wet location. But just be careful because sometimes in the larger size conductors, you might just get straight THHN insulation. And if that's the case, you're not permitted to install those conductors in a raceway underground. Well, what about XHHW? What does X mean? Well, X means that the insulation is made of thermoset, not thermoplastic. Two H's indicate a 90 degrees C maximum operating temperature, and the W indicates that it's listed for use in a wet location. What's the difference between thermoplastic and thermoset? Well, I'll use the analogy for thermoplastic of a piece of chocolate. When it heats up, it first becomes soft and then it begins to melt and turn into a liquid form. When it turns to the liquid form, it'll drip off of the conductor, land on the surface below it, form a puddle, and when it cools down, it'll harden back up in the form of that puddle. Thermoset insulation does not do that. When the maximum temperature rating of thermoset insulation is exceeded, it doesn't drip off like thermoplastic. It does become damaged. It generally discolors and kind of cracks and so forth. It definitely does become damaged, but it doesn't drip off like the thermoplastic would. Now, that thermoset insulation is a little bit more rugged, more robust than thermoplastic. It can take a little bit more abuse. Therefore, many times on your larger size conductors, you'll see thermoset insulation, XHHW, because the larger conductors generally take a little bit more abuse on the install. That thermoset insulation can handle that abuse a little bit better than the thermoplastic can. But remember, the maximum operating temperature of a conductor must not be exceeded. Therefore, proper design is of the utmost importance. Let's do a quick example. Suppose we have a 6 American wire gauge copper conductor with TW insulation, 60 degrees C insulation, installed in a raceway. And that raceway has a total of not more than 3 current carrying conductors. And the raceway, the pipe, is installed in an area where the ambient or surrounding air temperature is about 86 degrees Fahrenheit. Those are the conditions that the table is based on. So, in that situation, not more than 3 current carrying conductors installed in a circuit that's run in an area where the ambient or surrounding air temperature does not exceed 86 degrees Fahrenheit, well, then we can take the ampacity right from table 31016, 60 degrees C column, because that's where TW insulation is found. We can take that ampacity right from the 60 degrees C column of table 31016 and go with it. Now, if we were to look at table 310.16 and we reference a number 6 size, 6 American wire gauge copper conductor size, with the 60 degrees C column, we'll see that the ampacity, the maximum permitted ampacity for that conductor is 55 amperes. If this amount of current, the 55 amperes, is permitted to flow along the conductor, and then you were to take a thermometer and touch the conductor's insulation, the thermometer would read or indicate that the insulation has reached a temperature of 60 degrees C. which is the maximum operating temperature for TW insulation. Now let's say we take the same exact installation as we just covered, but now we allow the current from the 75 degrees C column to flow, which is 65 amperes, 10 more amperes. We allow that 65 amperes to flow in that circuit, and then we take a thermometer and touch the insulation. Well, now the insulation would read 75 degrees C, which would exceed that TW insulation's 60 degrees C maximum operating temperature. Conductors are exposed to multiple heat sources, but there are two primary sources of heat, and both of those primary heat sources must be considered when calculating a conductor's permitted ampacity. Keep in mind that if we were to place a spool of wire in a room, an area that has an ambient or surrounding air temperature of about 60 degrees, 60 degrees C, 30 degrees C, 86 degrees Fahrenheit, that spool of wire will eventually reach a temperature of 86 degrees Fahrenheit, even though we haven't even installed it yet. It's just sitting in a coil in the room. Temperatures tend to even out. We haven't even connected it to a source of power. We haven't installed it. All we did was we took that coil of wire and we put it in a room where the ambient or surrounding air temperature is 86 degrees Fahrenheit. That insulation will eventually reach a temperature of 86 degrees Fahrenheit. If the wire has TW insulation, 60 degrees C, 140 Fahrenheit rated, then we can only have an additional 54 degrees Fahrenheit that we can add to that conductor before we exceed its maximum temperature rating, its insulation's maximum temperature rating. How did I come up with that value? Well, we take the conductor's insulation's maximum temperature rating, 60 degrees C, 140 Fahrenheit, subtract the room temperature, 86 degrees Fahrenheit. So 140 minus 86 equals 54. So as you can see, if the ambient or surrounding air temperature where we install our circuitry is higher than 86 degrees Fahrenheit, then we cannot allow as much current to flow in that wire. Because whenever current flows along a conductor, heat is generated in that conductor. And the amount of heat that's generated in a conductor from the flow of current is exponentially proportional to the amount of current. What does that mean? Well, exponentially proportional means that as the current increases, the amount of heat generated increases at a faster or higher rate. But to keep things simple, let's just agree that more current means more heat, less current means less heat. Let's do a couple of examples. The following examples will explain how to properly calculate a conductor's ampacity when you have installation conditions that differ from what the table ampacities are based on. Example 1. What is the permitted ampacity for a 10 gauge copper, 10 American wire gauge copper conductor that has THHN insulation on it if it's installed in a piece of EMT and the EMT has a total of 6 current carrying conductors? And let's say the EMT is run through an area that has an ambient or room temperature of 110 degrees Fahrenheit. How do we solve, or how do we calculate this conductor's insulation, maximum ampacity? Solution. We go to table 310.16. We go to the 90 degree C column because we're using 90 degree insulation, THHN. From that 90 degree C column of table 310.16, we see that the number 10 gauge copper conductor has an ampacity of 40 amperes. But remember, this ampacity is contingent upon that conductor being installed in an area that has a surrounding air temperature of about 86 degrees Fahrenheit, and we have not more than a total of 3 current carrying conductors in that raceway, that pipe. So, in our example, we will have to adjust or derate the ampacity from the table because the raceway in this example has 6 current carrying conductors. The table ampacity is based on not more than 3. In our example, we're going to have 6. Even if all of those wires are different sizes, if we have more than 3 total current carrying conductors, we're going to have to adjust or derate the ampacity from the table. Located at the bottom of table 310.16, there's a note that tells us to see table 310.15C1. We can see that table 310.15C1, in the upper right-hand column of corner of this slide. When we go to that table, it indicates that if we have 4 through 6 current carrying conductors, then we have to derate or adjust our ampacity down to 80% of its table ampacity to compensate for the heat that will be generated from the flow of current in the additional conductors, the additional wires. Again, the table ampacity is based on 3, not more than 3. We have 6. So we take the ampacity from the 90 degrees C column for a number 10, table 310.16, indicated 40 amperes. We multiply the 40 amperes times 0.8. 0.8 is the decimal equivalent of 80%. 40 times 0.8 brings us down to 32 amperes. But we are not done yet. Remember, the ampacities stated in table 310.16 are also based on the wiring being installed in an area where the ambient or surrounding air temperature will not exceed 86 degrees Fahrenheit, 30 degrees Celsius. In our example, we stated that the pipe, the EMT, was installed in an area where the ambient or surrounding air temperature will reach 110 degrees Fahrenheit. So we will have to apply an additional correction factor to compensate for this condition as well. Located at the bottom of table 310.16, there's a second note that tells us to see table 310.15b for ambient temperature correction factors when our wiring is installed in an area where the ambient or surrounding air temperature is other than 86 degrees Fahrenheit, 30 degrees Celsius. The table, when we look to the table, and again, we have a copy of the table on the right-hand side of the slide here. There we see 4 columns. Going left to right, we have a 60-degree column, a 75-degree C column, and a 90-degree C column. Which column do we use? Well, whatever column correlates with our conductor's insulation's maximum temperature rating. In this example, we stated we would be using THHN insulation. THHN insulation, two H's, has a 90 degrees C maximum operating temperature. So we're going to use the 90 degrees C column. Now the fourth column to the right indicates or gives us the different ambient or surrounding air temperatures. In our example, our ambient surrounding air temperature was 110 Fahrenheit. We find 110 Fahrenheit falls in the 105 to 113 row. So we slide our finger across that 105 to 113 row over to the 90 degrees C column, and that indicates that we have to apply an ambient temperature correction factor of 0.87. And again, that's in addition to the derating that we had to do for the additional wires in that pipe. So 40 amperes, the ampacity from table 31016, 90-degree column for a 10 American wire gauge copper conductor, times 0.8, the 80% adjustment or derating factor for the 6 current carrying conductors. 40 times 0.8 brought us down to 32 amperes. 32 amperes times 0.87, which is the correction factor for our 110 degree Fahrenheit ambient or surrounding air temperature. 32 times 0.87 brings us down to 27.84. We can round that up to 28 amperes. Now, if we had just gone to the table and we grabbed the ampacity for a number 10, it would have indicated 40 amperes. But when we did our calculations in accordance with section 310.16, under these installation conditions, we cannot exceed 28 amperes for this number 10. Big difference. So again, to recap, if we have 6 10 American wire gauge copper conductors with THHN 90 degrees C insulation in a run of EMT, let me back up. If we have 6 number 10 American wire gauge copper conductors with THHN 90 degrees C maximum temperature rated insulation installed in a run of EMT, and that EMT is installed in an area where the ambient or surrounding air temperature will reach 110 degrees Fahrenheit, the conductor's new ampacity, based on the stated installation conditions, is 28 amperes. If we exceed 28 amperes, the conductor's insulation's maximum temperature rating will be exceeded, potentially causing catastrophic damage to the conductor's insulation. Let's do another example. What is the permitted ampacity for a 3 American wire gauge copper conductor that has THW or 75 degrees C insulation? If it is installed in a run of EMT that has a total of 9 current carrying conductors, and the EMT is run through an area where the ambient or surrounding air temperature will reach 120 degrees Fahrenheit. Now again, keep in mind, the ampacities from table 310.16 are based on not more than 3 current carrying conductors. We have 9. The ampacities in table 310.16 are based on the wiring being installed in an area that has an ambient or surrounding air temperature of about 86 degrees Fahrenheit. Our circuit is going to be installed in an area where the ambient or surrounding air temperature will be 120 degrees Fahrenheit, possibly an attic, a boiler room, a mechanical room, an electrical room, as well as other areas that may have an elevated temperature, ambient or surrounding air temperature. What's our solution for this example? Well, we go to table 310.16. We see that for a 3 American wire gauge copper conductor with THW 75 degrees C rated insulation, from that 75 degrees C column, we see it has that number 3 has an ampacity of 100 amperes. But this ampacity is contingent upon the wire being installed in a raceway that has not more than 3 current carrying conductors. So we will have to derate this ampacity because in our example, we have a total of 9 current carrying conductors. Underneath, at the bottom of table 310.16, we see a note that tells us to see table 310.15 C1 for the adjustment factors for more than 3 current carrying conductors in our cable or raceway. When we look to table 310.15 C1, we see that for 7 through 9 current carrying conductors, we have to derate down to 70% of the table 310.16 stated ampacity. So we take the ampacity for the number 3 from table 310.16, 75 degrees C column, 100 amperes. We multiply that ampacity, we multiply that 100 amperes by 0.7, 0.7 being the decimal equivalent of 70%. 100 times 0.7 drops us down to 70 amperes. That's a 30 ampere difference to compensate for the additional heat that will be generated in that pipe from the 9 current carrying conductors. Again, the table's based on not more than 3. We have 9. So we already had to derate current from 100 down to 70 amperes. But we are not done yet. Remember, the ampacities stated in table 310.16 are also based on the circuitry, the wiring, being installed in an area where the ambient or surrounding air temperature is about 86 degrees Fahrenheit, 30 degrees Celsius. In our example, it states that the EMT will be installed in an area where the ambient temperature will be about 120 degrees Fahrenheit. So we will have to apply an additional correction factor to compensate for this condition as well. In addition to the derating that we did for the number of wires, we will have to also adjust for that higher ambient or surrounding air temperature. Located at the bottom of table 310.16 is a note that tells us to see table 310.15b for ambient temperature correction factors when our wiring is installed in an area where the ambient or surrounding air temperature is other than 86 degrees Fahrenheit. When we go to table 310.15b, and again, we have a copy of the table here on the right-hand side of the slide. When we look at table 310.15b, in this example, we're going to go to the 75 degrees C column because we're using a wire that has 75 degrees C rated insulation, THW. We go to the far right-hand column. We find 120 degrees Fahrenheit in the 114 through 122 row. And when we slide our finger across that 114 to 122 row over to the 75 degrees C column, it indicates we have to apply a correction factor of 0.75. This correction factor is in addition to the derating that we applied for the number of additional conductors. So 100 amperes, the table 310.16 ampacity from the 75-degree column for a number 3, times 0.7, the decimal equivalent of 70% that we have to apply because we have 9 current carrying conductors. The table's based on 3. We have 9 of them. 100 times 0.7 drops us down to 70 amperes. But now, because the wiring is installed in an area where the ambient or surrounding air temperature will be 120 degrees Fahrenheit, we have to apply an ambient temperature correction factor. We went to table 310.15b, 310.15c, 310.15b, and it told us that for an ambient or surrounding air temperature of 120 degrees Fahrenheit, we had to apply a 0.75 ambient temperature correction factor. So we took the 70 amps times 0.75. That dropped us down to 52.5 amperes, rounded up to 53. So if we have 9 3 American wire gauge copper conductors installed in a run of EMT, and that EMT is installed in an area where the ambient or surrounding air temperature will be about 120 degrees Fahrenheit, the conductor's new ampacity, based on the stated installation conditions, is now 53 amperes. We went from 100 amperes down to 53. That is quite a difference. Hopefully you can see that if you just went to the table and did not take the installation conditions into account, you could be running into trouble. You size it based on 100 amps when the correct ampacity under these conditions is 53. If we exceed 53 amperes, the conductor's insulation's maximum operating temperature will be exceeded, potentially causing catastrophic damage. Now, in some situations, you may have different conditions along the circuit length. Let's say we have a relatively long run of EMT. We have junction boxes inserted, and maybe in the middle of the circuit, or maybe from the panel board to the first junction box, maybe we pull additional conductors in there. Point being, maybe we have 3 current carrying conductors in part of the circuit and 9 current carrying conductors in another part of the circuit. We drop one circuit off at a certain location and we continue the other circuit to our intended location. Or maybe the pipe run has to cut through an area with an elevated temperature. Maybe it has to cut through a boiler room, or cut through a mechanical room, or cut through an attic, or whatever. We're going to have different ampacities applicable to different portions of that circuit. So in those situations where the circuit installation conditions differ along the circuit length, such as, again, where we have a higher number of current carrying conductors in a segment of the circuit, or segments of the circuit are run through an area that have an elevated ambient or surrounding air temperature, the higher ampacity is permitted to be used if the portion of the circuit with the lower ampacity does not exceed the lesser of either 10 feet or 10% of the total circuit length. Now that is stated in section 310.14A2 in the exception. Hopefully that makes sense. So, hopefully, as you can see, the ampacity from the table, more often than not, must be amended based on the actual installation conditions. You also have to consider the temperature rating of the terminals or the lugs where you land your wire. The temperature limitations of the terminals or lugs where we land our conductors also must be considered when you're trying to determine the maximum conductor ampacity. Section 110.14c applies to the temperature limitations of the terminations where we land our conductors. I have an additional video that covers the requirements of 110.14c. It probably would be a good idea if you don't have a thorough understanding of how to properly apply the provisions of section 110.14c, I'd suggest you take a look at my other video applying 110.14c terminal temperature limitations. That'll give you info on additional restrictions on conductor ampacity.